All right, awesome. How's everyone doing?
Good.
Okay, I guess, but disappointed.
Disappointed?
Yeah, I didn't do as well as I thought on the homework, but I knew that like the first two problems I basically just tanked because of my misunderstanding.
Yeah. So we're gonna go over the homework today, and um, people seem to have trouble with different parts of that, kind of across the board. And that's the main reason I decided to postpone the midterm till Tuesday, which hopefully everybody got the announcement on yesterday, just to give us some more chance to go over some of these things like writing conditionals and flowcharting and stuff like that. And I really want to make sure that everybody like knows how to do these things because then you can just nail it on the midterm and everybody gets an A and life is good. So I really don't like changing dates on things like exams or due dates, but once in a while it seems like it's worth the whatever inconvenience or disruption it costs. Um, so hopefully that's a good thing. All right, no sleep. That's a bummer. Yeah, and so if the D bit is backwards, that's an easy thing to correct, right? Just you know, make a note and flip it over. Um, so let's start with that, right? If you say something like increment file register x, that means x equals x plus 1. And this equal sign in programming means the left side is assigned the value of the right side. And that's probably the first thing to make sure we're clear on because occasionally I get students even in like CSE 224 who get this reversed, right? So I knew a teacher once who called this the goes into operator. So x plus 1 goes into x, right? So this says take the value of this and assign it to x. So increment f takes x plus 1 puts it back into x. If you say increment f x comma w, that says w gets set equal to x plus 1. So without any extra operand here, this is both the source and the destination of the instruction. If you put a comma w, then x is the source, but w is the destination. And that's really all you need. Now you can also say comma f, and that's the same thing as not putting anything in. You can say comma f, I believe, and it says x equals x plus 1. If you do this with magic numbers, right, w is equal to 1, f is equal to 0. So if you say comma 0, it's just like not having an operand at all, and it's saying make x both the source and the destination. If you say comma 1, then it makes w the destination. But if you just stick with comma w for this and nothing for that, then you don't have to remember 1 or 0. And we're going to talk more about magic numbers today and ways to avoid them. Magic numbers are just, why is it a 1 instead of a 0? There's no reason. There's nothing, inherent in physics or mathematics that says this should be a 1 for the W register. It's totally arbitrary. So that's what I call a magic number. And there's lots of magic numbers that we encounter in microprocessors. So it's nice to have a symbol like W, and W means W register, right? So it's easier to remember and so on. All right, so let's see. So I posted your homework. I looked in detail at a few questions 10, 32, 33, 35, 36, 37, and 40. And those are the main ones that I graded. And in some cases, I glanced at some of the others. But it would be good to go through anything that you were unsure about on the homework, whether it was graded or not. And I plan to go through 32 and 35 through 40 in detail. Um,
I have a question about 10.
Excellent.
I, I think I know exactly what I did wrong now that I read what your message was on mine.
Okay.
Um, I mistakenly answered 10 times rather than 9 times.
Okay.
Um, and I also think we are supposed to write out the entire binary coding for a clearf instruction. but those were the addresses we were supposed to use, right?
All I needed to see was a 1 or a 0 for the access bit. So you didn't have to write out the whole clearf instruction. But I think yours was the one where you just had 10 ones and zeros, one on top of each other.
Yeah.
And so it's a little more typing, but if you copy and paste, it's probably not too bad. It would be a little clearer if you said, 0x00 colon and told me the value, 0x44 colon and told me the value. And normally I'd go through your zeros and ones and I'd line it up myself. But then since you had 10 of them, I didn't know which ones went with which, so that made it a little harder.
I think it was a typo I made, and that should have been more clear.
Okay, no problem. So let's talk about the access bit. Remember, the access bit says when we specify 8 bits of an operand, where do these upper 4 bits come from? And there's two possibilities. Possibility 1, we just make these zeros. All right? Doesn't matter what these 8 bits are. The 12-bit address of the file register is 4 zeros followed by the 8 bits we specified. And if we think of these as, bit 7, bit 6, bit 5, and so on, those are the 8 bits in the instruction. This would be the 12-bit file register address. All right? This is what happens when we set the access bit to 1. It says, 4 zeros followed by the 8 bits that were specified. If we set the access bit to 0, then our 12-bit address looks like this. All right, we have the 8 bits we specified in the instruction. This 8th bit gets replicated 4 more times. It's what we call sign extension. If this is a 0, these will be 4 zeros. If this is a 1, this will be 4 ones. And so if you want your address to... Sorry, go ahead.
I am a little confused about that. Why?
Why does it do that?
Yeah.
Because sometimes we want to access locations like 080, which is a general purpose file register. We usually just call it 80, but if we put zeros on the left, it's still 80. This is a general purpose file register. And we have 256 general purpose file registers. They go from 000 through 0FF. And so for all of those, we want a 12-bit address, where these upper 4 bits are zeros. So we definitely need to be able to specify that. But all of the special function registers, they all start with an F. FC3, FD2, F80. Right? All the special function registers, we need to be able to specify ones up here. So really, we only need to do 2 things on this processor. To make a 12-bit address, we're going to specify 8 bits, and then we need to either put in 4 zeros or 4 ones. And the mechanism for doing that is to use the single bit A. It just happens to be backwards. If we make this a 1, these are zeros. If we make it a 0, these are ones.
I have a question.
Mm-hmm.
So the only instance that A would be 1 would be for the first 4 bits to be 0, and then F7 would have to be a 1.
So if not exactly. So any time that you want an address where the first 4 bits are 0, you can do it by setting A equal to 1. You can sometimes do it by setting A equal to 0. Why? If this bit here, bit 7, happens to be a 0, and I set A equal to 0, well, if that's a 0, these are going to be zeros.
So.
Oh, okay. That makes sense. Thank you.
Mm-hmm.
Curious about something.
Okay.
In 10, it says that we're supposed to look at these magic numbers and given a clear F instruction on them, what the access bit would be. On 0x00, I assume it's 0, and then it's cleared and it's all 0. I remember you saying that it was probably a 1?
0x00, we could do, well, let's take a look at it. Suppose you code the instruction clearf 0x00. Suppose these 8 bits are all zeros. And we want to know what the 12-bit address is. Well, if we set the access bit to 1, we've said those 4 bits are going to be zeros. So the 12-bit address that we're going to clear is, hex 000. But suppose we set the access bit to 0. Well, our guide here says take whatever this most significant of the 8 bits is and replicate that here. Well, since this bit is a 0, these bits are going to be 0. Again, the 12-bit address is hex 000. So for this particular address, say again?
So a bit is both 0 and 1 in that?
A bit is allowed to be 0 or 1. When you code your instruction, a bit is a bit. It's got a value. But it doesn't matter in this case whether you code it as a 0 or a 1. They're both going to resolve to the same 12-bit address, which is 000.
What on earth?
So is the reason for that where sometimes, depending on your most significant bit, you want to use 0 because then it'll change from 0 to F?
It's more kind of just a kind of coincidental side effect. I don't think there's a deliberate reason why this is a possibility to use a 1 or a 0. It just kind of happens, right? And I don't know which MP lab prefers, but it makes no difference in the grand scheme whether I code the access bit with a 1 or a 0 if I want to clear this. So there's actually 2 different 16-bit binary machine language instructions that will do exactly the same thing. Clear file register 000. And it just kind of happens that's the way that it unfolds. But mainly when we use the access bit, what we're trying to do is force these bits to be 1s. And if you look at all the special function registers, this bit right here is always a 1. Right? The special function registers go from F80 through FFF. Now what if we wanted to access... What if we wanted to do something like this? Right, we wanted to clear F20. There's no way to do that on this processor. Because the only way we can get these upper bits to be 1 is by setting the access bit to 0 and making sure this bit is a 1. Well, if we expand 20, that looks like this. And it's just like 00. Whether we make the access bit a 1 or a 0, these upper bits are going to end up being zeros. So on this chip in particular, there's no way to clear file register F20. But that's okay, because there is no file register F20.
I think I'm having an issue between the naming convention and the memory convention, because I'm looking at OXF20 and those 4 zeros should be 1s.
Yeah.
So I'm confused why there's 0.
This is a counterexample. I'm saying there's no way to code on the PIC processor an instruction that says clear F20. Because you're exactly right. If we wanted to clear F20, this is what we should be clearing. But with this convention of using the access bit, there's no way to generate this 12-bit address. Right? It's just not possible. If I set A equal to 1, that's going to make these upper bits 0. And if I make A equal to 0, it's going to make these upper bits a copy of this bit, and this bit is a 0, so it's again going to make these zeros. So no matter how I set the access bit... Say again?
There's no way to hand it a 12-bit address.
There's no way to hand it this particular 12-bit address. Right? I mean, I could code it in the move FF instruction, but in the general instructions like, increment F or clear F, you have to use this access bit, and we can only set these bits to be a 1 if this bit right here happens to be a 1 also.
So that bit has to be a 1 in order for us to clear it.
This bit has to be a 1 in order for us to specify a file register where these bits are also 1. So this is strictly looking at operands, right? Nothing to do with clear or increment or anything like that. We're just looking at how do we specify a 12-bit operand when we only have 8 bits. That's the whole question here. You're allowed to specify 8 bits in the coding of the instruction. How do you specify a 12-bit address? Well, we use a single extra bit, a 9th bit, called the access bit. And if we set it to 1, it'll make these upper bits 0. If we set it to 0, it'll make these upper bits the same as whatever this bit is.
So basically F20 is just inaccessible or doesn't exist?
F20 is inaccessible, and in fact it doesn't exist. So you can't do this.
For those F80s or FFF and all of that, they'd all just be 0 because they would be inoperable?
So if you want to clear like FFF, alright, so we want to clear this 12-bit address. And so go back to our coding scheme. If we set the access bit to 1, can we specify this address? Definitely not. Because if we set A equal to 1, these upper 4 bits are all going to be zeros. So we can't set A equal to 1. But if we set A equal to 0, maybe we'll get lucky. So if we set A equal to 0, and we specify these 8 bits, what does this say? It says take this leftmost bit 1, replicate it over here. So this 8-bit pattern with A equal to 1 will give us this 12-bit address. So yeah, to clear hex FFF, we want to set A equal to 0. So I can give it to you as a rule, but rules are usually not very insight producing. But here's a rule. If you're going 0, 0, 0 through 0, 7F, you can set your access bit however you like. If you're going 0, 8, 0 through FF, you have to set your access bit to 1. And if you're going F8, 0 through FFF, you have to set your access bit to 0. So in a pinch, you know, someone gives you $1 million if you can answer this question correctly. What should I set the access bit to? You can go from a table, but it's not just a random, you know, this is how it works. This is how it works because what you're doing is you're taking that 8th bit and you're extending it into these upper 4 positions when A is equal to 0. But, you know, for working purposes, if you want to just kind of go with a table like this, put it on your notes or something, that'll get you by. And like I said, in practice, we never have to worry about the access bit anyway because the assembler sets it up for us. But, you know, you're bound to see a question somewhere on a test saying, you know, what would the access bit be for this instruction? Or given this access bit, what's the 12-bit address that we're accessing? So, but you can do it from here if you want. Does that help?
A little bit, but I'm trying to like figure out. I think my problem is that I have destination and like actual memory bungled up, so I need to figure that out. So
Well,
I'll talk to you after class about that.
okay. The thing to keep in mind is, you know, our file registers are specified with a 12-bit address, right? There's theoretically 4,096 file registers. Most of them don't exist. But, you know, these file registers exist, these file registers exist, and these file registers exist. And, you know, how do you tell the difference between 080 and F80? I mean, they both end with the same 8 bits, you know, a 1 followed by 7 zeros. And since all we get to code in our instructions are these, you know, last 8 bits, how could we make a difference between, you know, clearing this location and clearing that location? And the way we do that is we just use this single extra bit called the access bit. And it's because we don't have enough space in our instructions to actually store all 12 bits. If we did, we'd just store 12 bits F80 or store 12 bits 080. But rather than spend, you know, 12 bits, we spend 8 bits plus 1 extra bit. So it's basically 9 bits. Let us specify a 12-bit address.
This is how a lot of old video game systems used to get around not being able to access enough memory. They would just do bank switching like this.
Yeah, not even just the old ones, actually. Like Intel did this for a long time with memory banks or with segmented memory and so on. And if you go beyond, you know, the PIC 18F1220, if you look at other PIC processors, there's more than just these, you know, 256 general purpose registers. And there you start talking about 16 banks, and that really gets you into a deeper explanation of what the access bit is. It's really saying, do you want to use a bank select register or do you want to use what they call the access bank? But that's definitely further afield than we need to be. All right, well, I'll keep this sheet around and think about it and then come by lab hours if you want to go over it more. All right, and someone asked and someone else answered, what's the D bit? How do you find the D bit? So if D is 0, the result goes to WReg. If it's 1, it goes to the file reg, exactly. And you can not have to remember 1 or 0 by doing a comma W, right? W is a shortcut for 0. Or just doing nothing when you want a destination of 1, which is the file register. Oh, I'm doing stuff. There we go. All right, so let me let me talk quickly about the question 32. So where does code get stored in memory? So first thing to remember is we have 2 totally separate memories inside our PIC chip. We have our program memory, and then we have our data memory. So these are what we call our file registers. And this is our, you know, 256 general purpose registers and these other registers like Tris A and Port B and so on and so forth. And then physically separate from that, there's the program memory where we store our instructions. And this is much bigger than the data memory. The data memory is 256 general file registers. The program memory is a few K worth of instructions. And this separation of memory into 2 pieces, that's also a very RISC-based thing that ties into pipelining and efficient execution and so on. So the program memory, this is what we were asking in question 32. And there were some extra words in the assignment on Canvas that went with that. But determine the PC of each instruction in the following code segment. And in Canvas, I said basically what that means is tell me where in program memory each of these instructions is stored. All right. So the origin statement does not generate an executable piece of code. It doesn't get assembled into 1s and 0s. If you look at table 20-1, there's no binary coding for the origin statement, or for the word begin, or for the end statement, right? So these things begin, sub1, end, origin, config, radix, list, include, define, EQU. None of those things are actual instructions. So they don't generate any 1s and 0s that get stored in the program memory. So they don't change the address of anything in the program memory other than origin, which says where will the next instruction be stored. So if I just start listing a bunch of instructions, they're going to get stored at sequential locations in the program memory. So the origin statement doesn't actually store anything in program, but it does tell the assembler, when you get ready to store an instruction, store it at location 20. All right, so that's why the increment file gets stored at location 20. And then begin, that's just a label, but it doesn't take any space, so that doesn't use up any program memory. So it doesn't, change our address here. But then here's a call statement, and the call statement is going to generate, a pattern of ones and zeros. And so that's going to get stored immediately after the increment, which is at location 22. And the call is a weird instruction that takes 4 bytes, so it's actually going to sit at locations 22, 23, 24, and 25. And so the next location in memory is 26, and that's where the branch is going to go. And if we didn't say origin, then decrement would get stored at location 28, because that's the next location in memory. But because we say origin, we jump down to location 40. And that's where the next instruction will be stored. Well, sub 1 is not an instruction, so that doesn't get stored, it doesn't change anything. Here's a decrement instruction, where does it go? Location 40. And that takes 2 bytes, so the next location is 42, and that's a return instruction. So that's going to get stored right there. And then end doesn't get stored, because that's a directive. So that's what your map looks like. And then question 33 asks, if you replace the branch with a go-to, is that going to change your answer? And in fact, it's not. Right? If the question is asking what's the location where each of these instructions gets stored, well, if this branch becomes a go-to, it still gets stored at location 26. Now, it ends up taking more storage. It gets stored at locations 26, 27, and 28, 29, but it doesn't change where anything else is stored. Because the decrement doesn't get stored right after the branch or the go-to, it gets stored at location 40.
I have a question.
Okay.
As the code is being written, it looks like it's just going through the process in one straight line, but the code isn't going through a straight line, it's jumping from point to point. Why does it not increment as it's going through it versus, like, why is it doing it just in a straight line?
So awesome question. There's sort of 2 notions here that I often forget to mention, but we need to keep clear. There's the notion of compiling, or assembling in this case, of taking this code and figuring out what are the ones and zeros and where should they get stored in memory. Okay, this is what MPLab does when you hit that little hammer icon. And that has nothing to do with what the instructions are actually going to do when they execute. That's kind of a mechanical process of, here's an INCF, let's look in the table, here's the ones and zeros, this is something, where is that stored, here's the ones and zeros, right? Put this at location 20, that took 2 bytes, let's put this at location 22. Branch to begin, where was begin? Oh yeah, begin was at location 22, right? So nothing to do with the actual execution, the fact that this call is going to jump down here and change something on the stack, and this return is going to jump back. None of that affects how you take these instructions, change them into ones and zeros, and store them in program memory. And so in C or something high level, we call these things compile time operations. This is something that, GCC would do when you say GCC program.c. And the compiler does not have to understand what the behavior of the program is going to be when it runs. The fact that this call is going to cause us to jump from 22 down to 40, and then we're going to go to 42, and then after 42 we're going to jump back and we're going to go to location 26. Those are runtime or execution time notions, right? And that's what the CPU, the hardware inside the PIC, is doing in its little state machine. when the clock ticks and things get updated and so on and so forth. But those are really kind of separate concepts from each other.
I have a question.
Yeah.
That's okay. So I'm a little confused how the decrement instruction is assigned to 40 when you haven't even gone down, like, because when you call to sub 1, you're like, you left the begin loop.
Mm-hmm.
So it hasn't even like reached origin file register 40 yet.
Okay, also a good question. So when we hit the little hammer icon on MPLab, right, the code is not running. What MPLab is doing is it starts at the beginning, it goes through line by line, and it looks at each line and figures out where to store it, how to code it, and it does something so that it ends up at that right place in program memory. So call sub 1, well, it has to know where sub 1 is. We can talk about that later, but it codes a call, and then it's going to code this, right? Even if the call never came back to this statement, right, MPLab would still look at this and say, okay, this is a branch, it gets coded like this is begin, this is, PC plus 2 plus 2n, n should be such and such. And then it sees this and says, okay, now I'm going to start storing things starting at 40. It sees sub 1 and makes a note of that. It sees decrement, it says, let's store that at 40. Right? That's MPLab. That's not the PIC processor. That's just, something blindly going through and saying, let's translate each of these to machine code, and let's store them one after another in memory. And if we see origin, then, instead of storing this right after the branch, we'll store it at location 40 in this case.
So it can kind of like predict what's going to happen, pretty much.
It doesn't really care what's going to happen. So let's do a pathological example. Let's do something like this. We'll do an origin 10, and I'll say loop, and I'll say go to loop, and then I'll say increment file register 20 and decrement file register 40, and I'll say call loop, and I'll say end. Now if I type this into MPLab and I assemble it, we can tell exactly what it's going to do, what it's going to store in program memory where. Right, starting at location 0x10, it's going to store a go to, and that's going to take, locations 10 and 12. And then at location 14, it's going to store my increment. And at location 16, it's going to store my decrement. And at 18, it's going to store my call. In fact, when this code runs, right, as soon as it gets here, it's going to go back to loop. That's all it's going to do. It's never even going to get to any of these statements. But the assembler doesn't care about that. If it did get down here and call loop, it's going to go back up here, and it's just going to get here and loop forever, and eventually my stack's going to blow up. The assembler doesn't care about that. And if I had something down here like move ff a comma b, so call takes 0x18 0x1a, my move ff would go with 0x1c. Well, this instruction is never going to get executed anyway, because as I go through, when I get to call, I'm going to come back up here. So I'm never even going to get to that instruction. The assembler doesn't care about that either. The assembler is strictly looking at each instruction, converting it into machine code, and storing it at whatever location it should be stored at, which is usually just the next location unless you have an origin statement.
So, what happens, so if you go back to the homework example, what if you, kept linearly going down, and then you called it, or not called it, you origed it back, like let's say it was going linearly, and then you skip to 40, and then you go back to 20, but with a different instruction, does it overwrite it, or does it return an error?
It'll yell at you.
It'll yell at you.
Yeah. But, I could have done origin 40 and put these statements in the beginning, and then after that I could have said origin 20 and put these statements, And that would work perfectly fine, and it would end up doing exactly the same thing as what this code does.
So is the purpose of skipping around to keep things that are going to happen linearly next to each other in memory?
That could be. The main reason we're going to want for skipping around, though, has to do with what we call interrupts, which we're going to talk about today. And there's certain locations in program memory that are magic. And we already know one magic location. That's 0x00. So why is that a magic location in program memory? What's special about that particular location?
Nothing's before it.
Nothing's before it. What else? Everybody knows this, but I think you know it so well it's going to be hard for you to come up with it.
Is it technically because it's the reg file?
Not exactly.
What's the question again?
What is significant about location 0 in program memory?
Clear F.
Could be a clear F, but it could be, we could have any instruction in there.
The only thing I can think of is that it's attachment to reg, because whenever we say the destination is 0, it's reg. So, I don't know.
Right direction.
Is it just, because I don't know how the memory exactly works or what the memory map exactly looks like. It looks like between data memory and special functions that there is a large chunk, and I don't know if that's actually program memory, but I would think that 0x0 could be the first memory location after general registers.
That's a cool idea, and you would see that on some processors. On the PIC, they're actually completely separate memories. So program memory is not, hidden inside the data memory. Well, actually, it could be. I don't know what the architecture layout is, but in general, on a RISC processor, they would be physically separate memories, so that you could, read from here at the same time that you're reading from here, and not get a conflict.
And not have to fetch from too far away.
And not have to fetch from too far away. So when you run a program, what's the first instruction that it executes?
Your origin?
It looks like that, but remember, origin does not get compiled or assembled into machine code. So how would it know if my origin was 20 as opposed to 40? There'd have to be something that says, hey, for this program you should start at location 20, or 40, or 0.
Wouldn't it be... Go ahead.
Does that mean that it always starts at 0 no matter what?
Exactly. This is your first instruction.
Up until your actual origin statement, right?
Say again?
So, like, if you say start at origin 20, it's going to start at 0 anyway, but everything up to location 20 is going to be NOPs, right? No
It might be, it might not be.
Oh.
Right? So the physical PIC processor, the memory is non-volatile. So if you program in, something, and then somebody else takes the chip and they put this piece of code in, when they power up that chip, it's going to start at location 0, and it's going to execute whatever happens to be there, which in this case would be, whatever the last program was that got loaded in. So it's effectively random. So yeah, you're exactly right. Location 0 is the first instruction that's executed, and that's always the case on this processor. And for that reason, usually when we write code, we say something like origin 0 to say, hey, my code that I'm writing, I want it to get stored starting at location 0. Why? Because I want the processor to start executing my instructions, right? But if I wrote my program and I said origin 20, then it would still start from location 0. I just wouldn't know what it was doing. So 0 is one magic location. There's some other magic locations. Two of them we're going to talk about later today are locations 8 and locations 18. And these have to do with interrupts. And so when we're dealing with interrupts, we're going to sometimes want to put our code at 0, sometimes at 8, sometimes at 18. And sometimes we're going to want to put it somewhere far away from these so that we don't step on this stuff.
I have a question.
Okay.
If 0x00 is a magic number and that's where it starts every single time, why do we have to be very specific about what our origin is when we're making the code? And we can't just not add that in?
Because how would the assembler know that you were trying to write the instructions in the beginning of memory? It could assume that, but it's a bit of a dangerous assumption. So it's easier to just insist that the programmer always say where this should get stored in memory. But I mean, you could do it differently. You could simply say, if you don't specify the origin, let's just assume origin 0. And some languages do that. And some languages don't, and it just turns out on MPLab, as far as I know, last time I tried this, it doesn't assume an origin. So if you don't say origin something, I think it'll yell at you and say, hey, tell me where to put this stuff.
It absolutely yells at you.
Okay.
Yeah, I helped her debug some of the homework, and she had like 152 errors on
Cool.
one of her problems, and I was like, oh, you're missing a fork statement.
Yeah, your entire code will be errored if you don't have an origin. FYI.
Assembly language is good for that kind of thing. Somebody asked in chat if you had multiple ASM files, they all share the same memory space. Yeah, so if you broke your program into multiple pieces, right, you would use origin statements to basically say this piece goes here, that piece goes there, and so on, so that they fit together nicely. And you would start, your process by making yourself a memory map and saying, what am I going to have stored where, so that you can get to things. So on that quick reference guide, let me see if I can pull this up. Somewhere near the bottom, I believe. Or not. All right, let's try chapter 5. Yeah, figure 5-1. So here's a memory map for program memory. So location 0, that's called the reset vector. Reset vector is typically where the processor will start executing code whenever it resets. And there's various things that cause a reset. The most common one being when you first apply power to the system. And then location 8 is called the high priority interrupt vector, 18 is a low priority. And then here's all the locations that actually are available for your program in general. So going up to location FFF, right? This is all just program memory. And resets happen when you first apply power to the system, but also pin 4, that main clear pin, if you connect that to ground and then pull it back high, that'll reset the system. It'll go back to location 0. If you get a stack overflow or a stack underflow, that will reset the system. It'll go back to location 0. If the power drops below a certain threshold level, that's called a brownout, that will cause a reset. The system goes back to location 0. So 0 is where all the action starts. All right, so that's the business of memory maps for program memory. Go ahead and send me an attendance ping. Let me know you're here, and we'll do a 5-minute break. We'll come back. We'll talk about flowcharting and conditional statements in a little bit more detail with reference to what I saw on the homework. And then we'll go ahead and talk about some new stuff. So we'll come back in
Can
about.
I ask a question about the homework 4, if we have time?
Sure.
After the break, though.
Yeah, let's do it after the break so everybody can hear. Alright. Zoom is muted, but I'm still recording live.
Hello.
Is that a screaming eagle?
It is. I'm very hot mouth right now. But I'm not.
Screaming eagle.
Oh no, I know.
I think it's from refrigerators.
Oh.
You have your beach one with you.
Oh, that's right. You want me to bring you something?
Slip that in there, actually.
Want anything in my coffee or no?
No thank you.
Okay.
I run the air conditioning for 60 seconds. Alright, welcome back. Yeah, I'd say let's go ahead and talk about homework 4 question. If you're back.
Back. So I started working on homework 4 yesterday, and I got to, I think it was question 49, and I got a little confused because in the data sheet, when you use push or pull instructions,
Mm-hmm.
they don't want an operand, and or they don't care about the operand, right?
Yeah, so you're right. These are not the push and pop instructions that actually correspond to the pick processor. So it says draw an abstract stack.
The part that I found confusing is it's like push 20, push 10, pop 20, and I don't exactly know what it means by 10 and 20.
All right, so let's talk about abstract stacks. So I might have mentioned before, stacks are kind of a general computer science concept, and it's this idea of, you know, putting things one on top of another, pulling them off in the same order that you put them in on, so that the last thing you put on the top of the stack, that's the first thing you take off. So if we sort of imagined, you know, an empty stack as being empty, right? So there's nothing on it, and you say push 10, your stack now has a 10 on it. If you say push 20, and we can choose to draw the top of the stack at the top or the bottom of our picture. I'm going to put it at the top. So if I push a 20, our stack looks like this now. And maybe I can put a little indicator here saying this is the top of the stack. So anytime I push something onto my stack, it's going to go on top of whatever was previously on the top of the stack, and that thing I just pushed, that's the new top of the stack. Right, so this is that thing of plates that keeps pushing down as you put things on top, right? So if I pushed a 30, my stack would look like a 10, and a 20 and a 30 would be on the top. And then when you do a pop, it takes whatever is at the top of the stack and it pulls it off the stack. So now if I say pop, my stack looks like this. I'm back to just having the 10. The pop undoes the last push, which was the push 20. So now my stack looks like that. And now I think I said let's push a 10. And so there's the old 10, there's the new 10 that I just pushed, there's the top of the stack. You get what I'm doing? Now if I say pop, that top of the stack goes away, and my stack now has one thing on it, which is a 10. If I say pop again, my stack is empty. And if I say pop one more time, what do you think happens?
Underflow?
You get an underflow. It's a processor error. The CPU will reset. We'll go back to location 0 and start executing our program from the start.
So when you say push 10, you can't really do that in practicality without pushing 10 times.
So this is not this is not how push and pop work on the PIC processor. This is taking a step back and saying let's just talk about stacks. And then once you understand stacks and how things get pushed and pop, then we can look at the particular stack on the PIC processor, which is a simpler type of stack from this. In particular, you don't get to push a particular number on there. All you can say is push, and it pushes the address of the next instruction onto the stack. And so, for example, if let's draw a picture of our stack. So this is on the PIC processor now. So our stack has 31 locations. Isn't that Baskin Robbins? No, that's flavors. Stack location 0 doesn't exist. Alright, and there's this thing called stack pointer, which is initialized to 0 when we power up. And so let's say that we're in our program memory, and we're at location 20, and we say push. Alright, what a push instruction does on the PIC processor is it looks at the address of the next instruction in memory, and it pushes that onto the stack. So this instruction is a push, it takes 2 bytes, so our next instruction is at location 22. So this is pushing the number 22 onto the stack. And how does it do that? It increments the stack pointer, so it changes this to a 1, and then it stores the value that you're pushing, which is hex 22. And let's say I do some other stuff, and at some point, I find myself at location 44, and I do another push instruction. What value is going to get pushed on the stack if I'm executing this instruction right here?
I did some testing, and I think it just put 44 onward on top of the stack until it runs into a return, right?
So almost. This will actually push 46 because that's the address of the next instruction.
Right.
So that would become a 46, and the stack pointer gets incremented to 2. And let's suppose that I'm down here at location, 118, and I say call, some function blah. Well, a call is going to push something onto the stack. And what it's going to push is just like the push instruction. It's going to push the address of the next instruction. So if location 118 has a call, what is the address in program memory of the next instruction? This is tricky for 2 reasons. But take a shot and we'll work with it.
Well, if push is putting the next instruction on, call would just be putting the actual instruction you call onto the stack, right? So if you call location hex 48, that would be put on the stack, right? That would be the next thing it executes.
Not exactly. No. It's so we're back to question 32. It's not the address of the next instruction to be executed. It's the address of the next instruction in program memory. So go back to question 32 or whatever it was, right? Forget about the execution. If you look at program memory, right here is a call instruction. There's some instruction after that. I have no idea what it is, but what would be the address of whatever the next instruction was in program memory?
11C?
Yeah. Right, so the call takes 4 bytes, so it's 118, 119, 11A, 11B. The next instruction is at 11C. That's what gets pushed onto the stack, and the stack pointer gets incremented. Does it matter what this next instruction is? If this is an increment or a go to or a move FF or a halt and catch fire, does any of that change the fact that it's stored at location 11C? Absolutely not. So this is like, a compile time or an assemble time thing versus a runtime thing. The processor simply says, what's the location of the next instruction in program memory? Not the next instruction to be executed, but the next instruction stored. And maybe your program didn't specify any instruction after this in your assembly language. It's still going to store 11C. Okay, it's a very sort of dogmatic operation inside the mind of the CPU. And all it does is it says this is stored at 118, let's add 4 to that, put that on the stack. For a push, it's 2 bytes, so it says this is stored at location 20. Let's add 2, put that on the stack. This is at 44. Add 2, put it on the stack.
So a call is basically a push, only you give it a certain specification of bytes. So as in, I want to call something 20 bytes away, which is essentially push, but for 20 bytes.
So partially. So a call is like a push. It pushes the address of the next instruction onto the stack, but then it does a goto. So a call is really a push followed by a goto. Right? This is basically saying push and then go to blah.
That would make more sense to me.
Okay, good.
And this is sort of off topic, but file register 11C doesn't actually exist, right?
So this is an address in program memory. And we've got 4 kilobytes of program memory, so we can go from 0 up to whatever that is, 3FF or something. FFF, actually. 12 bits. So somewhere we're executing code, and we get to a return statement. What does return do? It looks at the stack pointer, it sees it's equal to 3. It comes to location 3. There's a 11C. It does a go to 11C. And in the process, it also decrements the stack pointer. So when we say return, the processor will go to location 11C. It doesn't matter where it is right now. It looks here, 11C, that's where it goes to. Where is that? It's right here. Guess what? The return brings you back to the statement after the call, which is what we want a return to do. Right? A call says, don't just go to blah, but, remember where you were. Take a little side trip to blah. And when you want to return right back here to the next instruction. That's the whole call return mechanism. Does that make more sense?
Seems like return, you shouldn't think of it as just resolving a function, but removing stuff from the stack.
Yeah,
So
definitely.
even if you didn't have a function that you called, if you run into a return, it's just going to remove the top thing from the stack.
Mm-hmm. And then if at some point you say pop is a really simple operation. All it does, decrement the stack pointer. And we can think of it as, removing whatever's at the top of the stack. So if the stack pointer is 2, 46 is at the top of the stack. If we say pop, it changes the stack pointer to 1. So now 22 is at the top of the stack. It removed this from the stack, basically, but it didn't do anything with it. It's purely just, adjusting the stack pointer. But we could think of a return as a pop followed by, go to whatever address was popped off. We don't use pushes and pops directly for anything in this course. They're useful if you want to do some funny things with the stack, but really the main way we use the stack is for calls and returns and for interrupts, which are really just another version of calls and returns. So mainly try to understand the call business and the return business. And this is the trickiest part, right? When you say call blah, it's not blah that gets pushed on the stack. It's 11C in this case, right? It's whatever instruction comes after the call, that instruction's address goes onto the stack. The reason being so that when we say return, we go back to the instruction after the call.
So I'm a bit confused when it comes to pop. So does it actually, so it doesn't actually delete the top of the stack, it just pushes the stack pointer back?
It just decrements the stack pointer, so this is still stored in the stack, but it says, the stack starts now with 22.
So you can't really use it to prevent stack overflows, right?
Not necessarily. I mean, stack overflows are kind of a pathological thing. And for example, if I said, bad, call bad, that'll cause a stack overflow pretty quickly. Because every time I call bad, I'll push the address of the next instruction on the stack, increment the stack pointer, and then go to where? Go to bad, which is going to do another call to bad. So after 31 calls, this is going to generate a stack overflow. Or if I said bad 2, push, and then go to bad 2, that's going to generate a stack overflow after 32 iterations of this. Because each time I push, it adds something to the stack, increments the stack pointer. And once the stack pointer exceeds 31, that's a stack overflow. Processor resets, go back to location 0, start over again. So there's...
Just a quick question.
Yeah.
What's the... On the homework, it's saying TOS register.
Yeah, I was about to do that. So this is the stack. Stack pointer is a register that's, you know, basically 5 bits, goes from 0 to 31, and it's got some flags in it. But then there's this other thing called the top of the stack. And the top of the stack is simply stack at whatever index is given by the stack pointer. So if stack pointer is 1, top of stack would be 22. If stack pointer was 3, top of stack would be 11C. So it's a way to look at the stack at the place that stack pointer is pointing to. And it's basically the thing that was last pushed onto the stack.
Generally speaking, we want to use a return instead of a pop.
Yeah, yeah. If you use a push for some reason, you'll probably use a pop at some point. But if you do a call, you're going to do a return. And the last funny thing to mention about top of stack, for example, if stack pointer is 3, top of stack would be equal to 11C, because that was the thing that got pushed on the stack, right? Well, 11C does not fit in 8 bits, right? This is at least a 9-bit number. It doesn't fit in 8 bits. Our special function registers are all 8 bits wide. So how can we store 11C in this thing called top of stack? Well, we can't. So top of stack is one of a number of registers that's actually broken into pieces. And there's a top of stack low, top of stack high, and a top of stack upper. And these just sort of get put side by side. And top of stack low is 8 bits. Top of stack high is 8 bits. Top of stack upper we can think of as 8 bits. And you put those together side by side and you can get, you know, in this case, a 24-bit number that we think of collectively as just being top of stack. It really maxes at 21 bits, but same idea. So usually we talk about top of stack, and in other courses we'll talk about top of stack or TOS. But on the PIC processor, because it's an 8-bit processor, TOS is actually 3 separate 8-bit registers. Top of stack low, high, and upper.
Does
Same.
the low get filled first, or not filled, but how does it put the numbers in?
So this is the least significant byte. This is the most significant byte.
Okay.
Yeah. And this is the same thing with the program counter, PC. Program counter says, where are we in program memory? As the program's executing, right, what's the address of the instruction we're at right now? Well, program counter is a special function register, but it's bigger than 8 bits. It's potentially 21 bits. So we have a program counter low, program counter high, and program counter upper. I think they have different names, but the same idea. We use 3 file registers to represent this one thing that we think of as a program counter.
Just in case we need to go somewhere really far.
Yeah, yeah.
Okay.
And if you get a nicer or bigger processor, right, it'll have, you know, a megabyte of program memory. You might want to jump to, you know, a location like 0x, you know, 2346. And that, you know, might be a valid, well, that wouldn't be a valid location. No, that would be valid, yeah. So the 18F1220 is a pretty simplified processor to work with because it's got so little data memory and so little program memory that we can sort of ignore a lot of these details, but they're lurking in the background. All right, so let's talk a little more about conditionals and flowcharts. And again, this is kind of a composite of some things I saw in the homework. But you know, ask questions, or if there's something I don't go over, make sure we talk about it. So some general comments first of all, and this wasn't clear, you know, in the way the homework was written, and it didn't cost you points, but general comments to keep in mind for the midterm in particular, right? If I give you a question which says, you know, write some pick code to do the following. If x is equal to 0, then y equals y plus 1. All right, so what I'm asking you to do in this kind of question is pretend that you are a compiler. You're a C compiler, right? You wake up one morning and it's like, hey, I'm a C compiler. People are giving me things like this, you know, and I'm supposed to write pick code for it. All right, so you make peace with that. So what do you do when you see a statement like this, right? What pick code do you generate that will perform this action? Okay, that's the basic mindset of these kinds of questions. And so you're not, you know, doing an origin statement because you don't know where this goes in the memory. You're not putting an end statement at the end. You're not defining port A and tris B, and you're not doing a config statement, which we're going to talk about today, but you're just writing a few lines of assembly language to correspond to this. The goal is, do you understand how to use what we've learned in pick assembly, conditional branches, increments, go-tos, things like that, to achieve this logical behavior? To check some file register called X, and if it's equal to 0, increment some file register called Y. Okay, and that's my goal in these questions, is to see you work with these pieces of logic. Now I could say, you know, design a control system for a coffee pot, and you would have to do this inside there, but that's a much larger problem, right? So I'm trying to just sort of see the parts and pieces, the building blocks. So you know, unless I say otherwise, you don't need to define what X and Y are. You don't need to set them equal to certain locations. You don't need to set your radix unless you're going to use, you know, the fact that you set your radix. You don't need to include P18F1220.inc unless you're using symbols from there, right? It's really just a few lines of code. You don't need to put it in MPLab. You don't need a disassembly listing. You don't need to simulate it. You don't need screenshots. I really just want a few lines of code. All right, so flowchart wise, what would this look like? Oh, and somebody asked last class how to draw the diamonds the right size to you know, have everything fit inside. So I mentioned that to Karina, my fiance. She's an artist. She said write the words first. So this is brilliant, right? So is X equal to 0? And that goes inside a diamond. And if yes, then we go down and we say y equals y plus 1. And if not, then we don't say y equals y plus 1. And if you see this statement inside C code, the understanding is that whether or not x is equal to 0, whether or not we increment y, what's going to happen next? Well, whatever comes after here, we're going to say, you know, call some function, or, you know, take the square root of something, right? Whatever happens in this statement, the next thing we're going to do is whatever the next statement is. That's what this is. And what happened before this? Well, I don't know, but, you know, something happened before this. And after that thing happened, now we're doing this if statement. So this chunk of a flowchart corresponds to this chunk of C code. And so you definitely don't want, for example, your no thing to go back up to the top. because that would be an infinite loop. That would say, if x is not 0, for the rest of the universe's lifespan, just sit here and spin forever, right? And that's not what you expect this statement to do. All right, so if you're writing snippets of code, then you don't have to, loop back to the beginning at the end of your snippet or something like that. You can assume this is part of a bigger piece. Let's see. If 0 branch, if not 0, x, else 0 branch, n 0. Then, yeah. I think I recognize your answer, and yes, that was totally awesome, the way you wrote those.
Cool.
Mm-hmm.
It's so much easier in my mind to read this.
It's nice to have labels that are meaningful to you, instead of just, L1, L2, that kind of thing, which is what a compiler usually produces, just sort of these uninspired labels. So BRA is unconditional. The request in the homework was not to use skip instructions. So when you're trying to do conditionals, you can use branch if 0, branch if not 0, but I didn't want you to use, test file and skip if 0, compare file and skip if equal, that kind of stuff.
My understanding was that when I was looking at the thing, the note thing,
Mm-hmm.
it stated that bra was an unconditional when I was reading it. So I was like, oh, so I can't use that. So I didn't use it in any of the coding.
Oh, okay. That might have been a bad choice of wording on my part. No, I the punchline of that note was don't use the skip instructions. So don't use test file and skip, decrement file and skip, that kind of stuff. When you need to do a condition, when you need to do a condition, use a conditional branch. But I didn't mean by that you should not use unconditional branches, because you do need to use those sometimes. Okay, well that makes a little more sense.
Unconditional in there. I was kind of like, how am I supposed to do that without branch? I mean, I can use go-to, so I use go-to for everything.
Yeah, which is okay. That works too. All right, sorry, bad presentation of that. All right, so does this make sense, this idea of a snippet of code, and why we don't want to have a loop that goes back up to the top or things like that? So if we wanted to write this in assembly language, how do we know if x is equal to 0? Well, we have to somehow, we're going to do a branch 0 or a branch not 0, right? But branch 0 doesn't mean, branch if x is 0. It means branch if the last thing that I did, whatever happened up here, caused a 0. Well, I don't know what happened up there. So if we want a branch based on whether x is 0, let's do something so that whether x is 0 or not somehow affects the 0 bit. And we can do almost anything we want with x. For example, we could say move x into the W register, and that touches the 0 bit, and then we could say branch if not 0, no increment. And so if x is equal to 0, we will not branch, and so here we can say increment file register y. So that's this piece over here. But if x was not equal to 0, we want to skip over that increment and come down somewhere else. So I can put no increment right here. So that's a perfectly reasonable coding of that flow.
So you mentioned how if we were taking the midterm, we could just answer like that. We don't need the radix hex or any
Right.
RG statements. We just need to do the flowchart statement.
Yeah, all I would need is the flowchart if I ask for it, and like that code.
Cool.
Now, if I want you to write a whole program, I'll say something like, write a complete program. And there you got to have, an include if you're using those definitions, and an org statement, and an end at the end, and so on and so forth.
Okay.
So I'll try to be really clear about it. And during the midterm, hopefully you're logged into Zoom and you're, in the classroom. And if there's ambiguities or questions, you can always send me a note and say, hey, what do you mean by this? So,
Okay.
but I'll try to make it clear. All right, so what can go wrong with this? If x is equal to 0, y equals y plus 1. So, move f x comma w, branch of 0, increment y, increment y, increment file register y. And this might feel like it corresponds to this flowchart, but it doesn't, right? This says see if x is equal to 0, and if it is, then we're going to jump down here and do our increment of y. But if it's not equal to 0, what is this code going to do? If it doesn't take this branch, what's going to happen?
It'll knock and then fall through.
If it doesn't take the branch, it will just go ahead to the next instruction, which is increment file register y. So if x is equal to 0, it's going to branch here and increment y. If x is not equal to 0, it's going to fall through and increment y. So in either case, y is going to be set equal to y plus 1. And so that's doing something like this. If x is equal to 0, y equals y plus 1, else y equals y plus 1, which is a totally different statement. This is really easy to do, by the way, right? I mean, we've all written code like this, meaning it to do one thing, but when you actually go through and play it line by line, it does something different. It's one of the challenges, one of the many challenges of assembly language, and it's a really easy mistake to make.
I think the reason why I could see, because I did it exactly the way that you just described.
Mm-hmm.
Well, my reasoning was that it feels like per box things are supposed to be separated or in their own junction.
Mm-hmm.
But I didn't realize that I had to connect the end pieces so that it just continues into one loop. I didn't know that was an option, and nor was it requested. So
Right.
it was kind of like, what am I supposed to do here at the end? Am I just supposed to let it hover in the air?
Yeah. and that's so that's why I went through, you know, this idea of doing snippets just now instead of putting a loop at the bottom and so on and so forth. This kind of thing is more of, you know, even if this was a whole self-contained program, it's still not doing the correct behavior, right? Because if I have my increment after the BZ, it's going to do the increment regardless of whether it branches or not, right? So if I was going to do something like this, what I might need to do is after my BZ, I might want, you know, a branch or a go to some other label, which would be down here. And then if it doesn't take the branch because x is not 0, this will say, okay, well, let's skip over the increment and come down here. And now we're doing that function.
I have a question.
Yeah.
So, some of the questions were saying things like, don't change x.
Mm-hmm.
Sure exactly what that means.
All right, so let's look at one of these. So if x minus 1 equals 0, then set y equal to y plus 1. So we want to subtract 1 from x and see if we end up with a 0, but we don't want to actually change the value of x. Right? If you write C code, you don't expect, suppose, you know, x is equal to 5, and then you do this if statement. After the if statement, x should still be equal to 5, right? Because this doesn't say change the value of x. It says let's just see if x is equal to 1, or if x minus 1 is equal to 0. So you could do something like, decrement file register X and branch if not 0, no increment. Otherwise, increment file register Y, and then here's our no increment. So if X minus 1 is not 0, we'll skip over this. If it is 0, then we'll go ahead and increment Y. The problem with this, though, is that this actually changes the value of X. If X was 5, then, it's not 0, it's not going to increment Y, but all of a sudden, X is equal to 4. And that's a bug in our compiler. So in this case, when I decrement, I would probably want to put the result back into W to change the value of the W register, but leave X intact.
I have a question.
Mm-hmm.
When we're reading the if x take away 1 equals to 0 and the y equals y plus 1, is
Mm-hmm.
it supposed to be reading it as an and or a then?
Then. So in C, you can either write this, or you can put this inside curly brackets. And in other languages or in pseudocode, you might put the word then, but this is the condition, and this is what you want to have happen if that condition is true.
Okay, thanks.
Yeah. And you might see something like this. If X is equal to 1, set Y equal to Y plus 1. Well, we don't have a conditional branch for if the 1 bit is set or something like that. We can see if something's 0, but it's harder to see if something's 1. So when you were trying to write code for this statement, you might change it into if X minus 1 is equal to 0. So if I asked you to write code for this, it would be exactly the same code as what you'd write for that. All right, let's see. So another thing I saw commonly, do some stuff, branch of 0 somewhere, and then somewhere is the next statement. Here again, whether or not the 0 bit is set, after we execute this statement, we're going to end up right here. So yeah, if the 0 bit is set, we're going to branch down to somewhere. But if the 0 bit is not set, guess what? We're still going to come down to somewhere. It's going to be the next thing we do. So usually, somewhere would be somewhere else other than the next instruction. If it's the next instruction, you don't even need a conditional branch. And the conditional branch actually doesn't do anything. It doesn't change your flow, because whether the 0 bit is set or not, this is still going to be the next instruction you do. All right, another thing.
So if the somewhere thing was on a midterm ring, could you just do like a bunch of lines under it to like say there'd be a bunch of code here, and then somewhere to signify that that somewhere's not directly after that?
Yeah, you could do that, or
before it.
Or don't even like specify this, right?
Okay.
So somewhere it's like X and Y, is set up somewhere. That's probably the easiest way. Is just don't choose to put the label somewhere. Don't put the label somewhere. How about that? Another thing, when you want to test to see if, say, X is equal to 0, we can actually just say move file register X. The destination bit, if we put a comma W, it changes the value of the W register. If we don't put a destination bit of W, this says set X equal to X. Well, that does no harm, and it preserves the W register because we're not stepping on the W register, but it does update the Z bit. And so we can simply say move FX, and then we can say branch if not 0 or branch if 0, depending on what we're trying to do. So that's always an option. Comma W works perfectly fine also, but if you were writing this as part of something bigger, you might be using W for something else, and this lets you do the same test without changing your W register. So that's a nice option on the PIC processor. Alright, another thing I saw sometimes, so if x equals 0, do something. So move x into W and then subtract WF x and then branch of 0. So what's the issue with this logic?
It will always be 0.
This will always be 0.
Itself.
This is saying wreg equals x, and this is saying, you know, x equals x minus x. Right? You're subtracting the wreg, which is x, from x. That's always going to set it equal to 0. And so my branch of 0 is always going to fire. It's basically an unconditional branch. Alright, move LW1. What does that instruction do?
Move literal.
Moves a literal. What's the literal value?
1.
1, and where does it put it?
Right.
Yep. So if you want a 1 in wreg, that's the way to do it. Now, if you start your program and you say add LW1, what does that do?
It adds the
Adds a
literal
literal
1.
1.
Adds a literal 1 to wreg. If you happen to know that wreg is 0 before you do this, this will set wreg to 1. But we don't know the value of wreg unless we've given it a value. So if you're in the beginning of a program and this is the first instruction, you have no idea what the value of wreg is. It might be 1, but it might be any of 255 other values, because your registers are not zeroed out at the beginning of your program. So if you want to put a particular value into W, make sure you use move LW, don't just add. Add would only work if we knew that W was 0 to begin with. They take the same amount of space, the same amount of time, so there's no reason you would hope that add would work instead of move. So make sure you know the difference between those. Alright, one more thing on flowcharts. So the thing we put inside this diamond is always a condition. And it always has two arrows coming off of it, a yes arrow and a no arrow. A rectangle is just some statement. And it has an arrow going into the top, an arrow coming out of the bottom. A condition, you know, has an arrow coming from the previous statement, and we basically choose to go off in one of two directions, based on the answer to some question. So this condition in here, this should always be a question. And so I'm seeing some things in here like x minus 1. Well, is x minus 1 a question? Can you answer x minus 1 with yes or no? It's an operation. So you wouldn't want to put x minus 1 in here. And you wouldn't want to put something like if x minus 1 equals 0, because that's not a question. I mean, what's the answer to if x minus 1 equals 0? I mean, I know what you're after here, but think of it in a very sort of like algorithmic way. Is this something that you can answer yes or no to? No. Now this is a question, right? Is x minus 1 equal to 0? So you could say, is x minus 1 equal to 0? So make sure when you write these things inside these diamonds, these conditions, they're what we call propositions. Something that can be answered yes or no. If you do CSE 215 with me probably next year, we'll talk a lot about propositions. And this will come up again when we do formal proofs. So the condition in here should be something with a yes or no answer. And then if the answer is yes, you come down the yes branch. If the answer is no, you come down to the no branch. And you know, it could be no over here and yes here, or you might come off both sides. You can draw it however you like. But there's always two arrows coming out of it, one labeled yes, one labeled no.
You mean next semester?
Yeah. 215 is in fall and winter. So if you're CS, you're taking 270, you're probably doing the 200 sequence next year. So fall and winter.
Yeah.
Cool. All right. Does that help any with flowcharts and conditionals?
A little bit.
This all makes way more sense now, thank you.
Okay. So there'll definitely be some of this on the midterm on Tuesday. So come by lab hours if you want to talk more about it today. And we can go through it some different ways. Let me tie up a few other loose ends. One of them is the config statement. So let me pull up a lab. Let me pull up lab 2. Was there any code for lab 2? No, there wasn't. Let's see. All right, let's look at lab 1. So most of the sample code that you see, yeah, there you go, thanks. Most of the code that you see has this sort of boilerplate stuff in the beginning, right? So, you know, you can put comments in the beginning to say, you know, who wrote this and what class and so on. The list statement, again, I don't think we need that in most cases, but we're going to have an include statement. And when you say include, then you do not want to say define. And definitely get out of the habit of using these defines for these special function registers, port, tris, addcon, all of those, right? These are what I call magic numbers. The include file, p18f1220.inc, defines all of these magic numbers for you. It does these defines for you, right? So do that include, and then don't put these defines in, right? And there's a lot of reasons for that. It's less typing on your part. It makes the code portable. It makes your code shorter so you don't have to look at all of this stuff. And it saves you from the horror of accidentally, you know, typing a 9 instead of an 8 here. And that's going to take you like 6 hours to find, right? Because that is such a bizarre, subtle bug. It's going to be really unpleasant. So don't define these special function registers. Just use that include statement. All right. You can use radix if you want. I suggest, you know, if you mean hex, say 0x. If you mean binary, say B quote. If you mean decimal, do D quote or put a period in front, right? Specify it in your code instead of relying on a default radix. But this statement down here we haven't talked about, config. And I don't think it makes any difference for us in the simulator. We want to put it in there anyway, but it definitely makes a difference when we run actual hardware. And config is an odd kind of statement. So I've said that, you know, there's assembler directives like list and radix and define, and then there's instructions like move WF, clear F, and so on. And I've said these instructions put code into the program memory, and these directives don't. All right, config also does not generate program memory code, but it does have an effect on the CPU. It basically tells the CPU to go into one of a number of different states that it can be in, and it kind of affects the overall behavior of the processor. And one of the things we can specify on this config line is the oscillator, the system clock. Right? And this lets us control where does that system clock, that heartbeat that keeps the whole program running, where does that come from? How fast does it run? How can we modify it? And so on and so forth. LVP, I'm not going to worry about. That has to do with how you program it and whether you need a high voltage or a low voltage and so on. But WDT equals off. This is one I want to talk about. So WDT is a watchdog timer. So what does a watchdog do? How many people have encountered a watchdog, say at a junkyard or something? Or cutting through someone's property for a shortcut. And a big dog on a heavy chain comes barking at you, right? That's a watchdog. So what does a watchdog do, right? It kind of hangs out in the background. Yeah. It hangs out in the background until something happens. And when some particular thing happens, it starts barking and snarling and tugging at the chain, right? Okay, there's a little tiny watchdog inside the PIC processor. And it hangs out most of the time and just sort of like sleeps. But what it does is, if a certain amount of time passes, it will wake up. And it'll bark and snarl and jump around, and it will cause the CPU to reset. And when the CPU resets, it starts over from the beginning. The watchdog is asleep. And after a certain amount of time, it's usually a few milliseconds, watchdog wakes up, barks, CPU resets. All right? And there's two ways to stop the dog from waking up. One, we can use a command which says, hey, let's reset the dog's timer. So if it's going to sleep for 10 milliseconds and 5 milliseconds have passed, we can say, hey, go ahead and reset the timer. And it'll go back to sleep for another 10 milliseconds. But we can totally turn off the watchdog so it never wakes up by doing this config WDT equals off. And that's what we normally put in the beginning of our programs. Now, why would we not do this? Why would we want a watchdog that wakes up every 10 milliseconds? It's a fail-safe. Yeah, go ahead.
Because if we're going through a process and we're taking our time with it, step by step, we don't want it to reset in the middle of it.
Mm-hmm. But when would we want the watchdog to wake up periodically?
I read into this a tiny bit,
Mm-hmm.
and I noticed that if you don't, every number of clock cycles, if you don't set the watchdog down or something, you completely reset the processor.
Right.
As in, like, let's say you had some industrial use for this PIC processor, and it was, if something didn't execute and that alerted the watchdog, you need to reset the system.
Yes, yes. So let's suppose you're building a microwave oven and you're controlling it with a PIC processor. And you're monitoring the keypads on the front, so when someone hits the one key, it generates 5 volts on RA0, and when they hit the start button, it generates 5 volts on RA4, and you've got buttons and you've got input pins to your processor, and you write some code. And the code, looks at those buttons and says, oh, they hit a 100 start, so I should run for 60 seconds. So you turn on the microwave generator, right, the magnetron, and you start, a delay loop, and every second you subtract 1 from something you initialize to 60, and when it gets down to 0, you'll call a function that sounds a beep, and you'll turn off the microwave generator. Okay? If something goes wrong in your program, and there's lots of things that can go wrong, right? You can get a stray alpha particle coming from a supernova somewhere, and it hits a bit in your special file register, and your counter for 60 seconds changes into something bizarre, or your program counter changes to something bizarre, right? and potentially, you know, you're trying to cook your microwave food for a minute and it turns the oven on and it never turns it off, you know, or it disables the off button, or, you know, all kinds of things. So what you can do is in your code, let's say you expect your code to periodically go through this loop that's, you know, counting down from 60 seconds down to 0. What you do is every time you go through that loop, you say, hey, watchdog, go back to sleep. And as long as you're in that loop doing what you expect your code to do, you keep soothing the watchdog and telling it to go to sleep. But let's say something happens and for some strange reason, your program counter jumps out of that loop and now you're running some random code that's not even yours. It's just, you know, a stray loop that happens to be in there. Well, what's going to happen is you're no longer executing this instruction that tells the watchdog to go back to sleep, and after a few milliseconds the dog will wake up, bark, CPU will reset. And in the beginning of your program, right, you check to see if you had a watchdog timeout, and if you do, you turn off the microwave generator and you throw a message up on the screen that says, you know, error 17. And now the system has failed in a controlled way. So watchdogs are like a safety thing that we find in a lot of microcontrollers. So this is, the PIC chip we work with is really intended to be used as an embedded controller. It's not something we would put inside a laptop. It's not something we would use to build a smartphone. It's really kind of a little control system, right? And a lot of control systems, microcontrollers, have safeties like a watchdog built in. And it basically forces you to know how long your loops take and make sure that you periodically soothe the watchdog. And then if something happens and you don't execute the code the way you were expecting it to, the watchdog will automatically wake up and reset the CPU. And you can use that to stop the system from just getting kind of hung up mysteriously. We don't do that in our code in this course, so we always turn the watchdog timer off. But if you take your code, like your 4-bit adder, and you put that on a physical chip, and you started running it, what would be happening is that every few, I think it's a few milliseconds usually, your CPU would reset. And you might never notice, except you might see, you know, a little flickering in the output. But, you know, if you clear the output in the beginning of your code, your adder would look like it wasn't working. Because, you know, as soon as it starts to run, it takes the inputs, it adds them together, it displays the output, and then the watchdog wakes up, barks, CPU goes back to the beginning, and your output port gets cleared. So that's what the business of the config statement is. And like I say, we just kind of like blindly put this into the beginning, and we just always do this up front. In our assembly language code, just like in the executable code, we're always going to put 7f into addcon1, and if we're doing I/O, we're going to set some value to tris B and or tris A. So that's what that business is. All right, other questions? All right, we got a few minutes left. So let me talk about the midterm on Tuesday. So the midterm will be Tuesday. I'm going to go ahead and do it at 12 o'clock because we've had enough time now to talk about the homework and so on. So midterm will be Tuesday at 12 o'clock till 1 o'clock. All right, so I'll post it sometime over the weekend and it will open up 12 o'clock. Please come to class as usual and sit in the Zoom room. I'll leave my microphone muted, but you know, if somebody says, hey, question 4 is impossible, and I say, oh yeah, this should be, you know, a 0 instead of a 1, well, I'll announce that to the class. I'll put it in chat, or I'll open my microphone and tell people. And if you're not in Zoom, you don't get to hear that, and I have no way to give corrections to you or clarifications. So please come into Zoom, and I'll keep my microphone quiet for the most part, but just in case I have to tell you some clarification on the exam. So the exam will go from 12 to 1. We'll take a 5-minute break at 1, and then we'll go ahead and lecture the second half of the class. So that's just kind of logistics on the midterm. Also, I clarified in Canvas, it's open book, open note, open data sheet. Okay? You can use your labs, you can use your old homeworks, and so on. What you can't use is MPLab, right? So don't use MPLab to assemble code or check syntax or anything like that. No online resources, no collaborative resources. All right, so and there's an honor statement in the beginning that you'll have to read and agree to that basically says that.
Can we just print our name?
Yeah, I'll have an honor statement, and the instructions will say, just write the word honor statement, colon, followed by your name on your exam, and that's your signature. All right, we got about 5 minutes. Let's start talking about interrupts, because interrupts is where things get really fun and interesting with microprocessors. And let me just give you kind of a general notion of what an interrupt is. So suppose you're waiting for a phone call, right? So you've applied for a job, and they're going to call you and let you know whether you got it. And they said, they're going to call sometime between 9 and 5 today. All right. So you really want to know if you got this job. You really want this job, right? And you've got your phone. So there's 2 ways that you can spend your day. One way would be to stare at your phone, right? To turn the screen on and just stare at it and wait and wait and wait for it to show you the message that says, call coming in, and then you can pick up the phone and talk to the person, right? And that's probably not a really great way to spend your day, okay? But you could do that. But the other option is, turn on a ringer so that when a call comes in, it makes a sound. And as long as you have the phone close enough that you can hear that sound, guess what? You can go about and do whatever you want during the day. Within reason. Maybe you can't run the vacuum, or the cement mixer, but within reason, right? You can work on homework, you can play video games, you can watch Netflix, whatever, right? And when a phone call comes in, guess what happens? The phone makes a noise, and that interrupts whatever you're doing. And you hear the sound, and you go and you look at your phone then. And it says, incoming call from Google. And you say, oh, there's my call, I'm going to pick it up, right? Or, incoming call from spammer, and you ignore it. All right? So all of these things are completely analogous to what goes on inside a microprocessor. And the system we're going to be working with starting next week is what's called the interrupt system. And interrupts are a way to basically tell the processor, hey, you can go about your day as usual. You can play video games, you can watch TV, right? But I've set something up that might happen. And if this thing happens, I want you to stop what you're doing and do something else. Deal with this thing. All right? And there's... Yeah, go ahead.
So would this be like, we have a pin for interrupt, and we trigger it when, we trigger it, and then we need to do some bit of code?
Exactly.
Okay.
And you could be, running your 4-bit adder, and your adder program is a loop. It looks at port B, it sees if the number has changed. If it hasn't, it goes back and looks again. If it has, it breaks it into 2 numbers, adds them, puts them out to port A, goes back to the top. That's an infinite loop, right? As it is, the code you wrote for Lab 2, that's all it's ever going to do. Take in 2 numbers, add them, put the sum out, right? But we could set something up in the beginning of the code which said, hey, but if somebody ever applies 5 volts to pin 9 of the PIC, I want you to do something else. I want you to remember where you were in your add algorithm, but pause that and come over here and do something else. Light up a light, ring a bell, turn on a motor, change the direction of something, right? And then when you're done, go back to where you were. That's an interrupt. And so we'll talk about how to set up interrupts, how to tell the system, hey, you might get a phone call, so be ready, and when you get it, do such and such a thing. We'll talk about how to respond to an interrupt. So how do you tell it to actually do something in response to that? And we'll talk about how to tell it to ignore an interrupt. so that, you know, maybe you're doing something really important, you're at a really, really good part in your game, you don't want to be interrupted, so you're going to temporarily, you know, turn your ringer off, or you're just going to ignore the ringer when it rings, right? So we can do that with a processor also. We can say ignore interrupts for a while, okay, now go back to paying attention to them. So that's the basic setup that we're going to do when we deal with interrupts. And interrupts are going to be a piece of machinery that we use for pretty much the rest of the course. Because then we're going to talk about doing things like working with timers and working with motor control systems and doing serial communication, and all of those things are going to use the interrupt subsystem to help do their job. So interrupts will be fundamental, and they'll use the notion of calls and returns, and they'll get us into where we can talk about things like side effects and all kinds of cool computer science-y concepts. And they'll let us do lots of bit manipulations, bit sets and bit clears, and lots of bit tests. So it'll be a springboard into a whole bunch of fun and interesting stuff. And you'll have some labs dealing with these. All right, so go ahead and send me one final attendance ping. And I will switch to my office hours in a few minutes, and I'll meet you in there if you got any questions and such. Otherwise, enjoy the rest of the weekend, and I will see you next week. Thank you so much.
Thank you. Have a great day.
Thanks.
Thank you.